Hi everybody. Today I'm going to run through using Stata to execute some simple bivariate hypothesis tests. Right? So some simple tests for checking the relationship or for the existence of a relationship between two variables only. Right? So I'm not going to cover regression here. I'm not going to cover more complex modes of analysis for dealing with confounders and things like that. I'm just going to cover three relatively common bivariate hypothesis tests. The Crosstab, or the chi-squared test, the difference of means test, the Ttest, and one-way analysis of variance, one-way ANOVA. Okay? So let's get started. So I've already loaded some data in. Right? So I've loaded in the 1978 automobile data that lives inside the Stata files, right? So with this sysuse auto command. So this has a bunch of different variables. And we can test some pretty simple hypotheses here. Right? So start with the Crosstab. So the two variables I'm going to use for this are foreign, right? Whether the car was an American-made car or a foreign car, and rep 78. The repair record in 1978. Now, rep 78 is kind of a mysterious variable in this data set, right? It's not well documented as to what it means, but it appears to be an ordinal variable. It appears to have 5 values in 5 categories. I'm going to guess it's categorical, perhaps ordinal, right? I'm going to guess that it's an ordinal variable. So for our purposes, I'm going to assume that it is 1 if the car had sort of the worst repair record, and 5 if it had the best repair record, right? So maybe it's 5 if it had very few problems, and 1 if it had an extreme amount of problems, right? If it just didn't work at all. Maybe that could be false, but for our purposes that will do. Okay. The other variable, foreign, is a simple dichotomous variable that is either 0, domestic, or 1, foreign. Okay. Domestic make, foreign make. So if I say I have variables like this, right? I have two variables that both come in categories. My dependent variable will be the repair record. So maybe I think that foreign cars in 1978 broke down less frequently than domestic cars. I can test that hypothesis, or that they at least didn't break down at the same rate. Okay, so I can test that hypothesis using a crosstab. Right? So when my dependent variable is categorical, I need to use the crosstab. Of these three methods, at least. So to run a crosstab, we're still going to use this tabulate command, right? It's going to still use tabulate. And technically, when you're doing a crosstab, the variables can come in any order. You can put them in any order you want, right? I generally put my independent variable first, followed by my dependent variable. And I'll explain why in a little bit. Right? So I usually go independent variable here, dependent variable, and then you need a comma, because we have to set some options, right? If I just do this command here, I'll wind up with a table, right, that will give me my two different car types and my repair records and a bunch of counts, but no actual hypothesis test. There's no statistics going on here, right? So if I want to actually add the statistics, I need to add the option chi2. And while I'm here, right, this chi2 actually runs the test. I also include the option column. Okay, and we'll see what that does here in a second. Right, so now what we have, if we run that line, we have our table expanded in 2 ways. Right? First way is this column option. Underneath each number in the table, we have the percent of that column that each cell represents, right? So if we have how many people in the of all the cars that were 4s, right, on repair records, so maybe I think that's pretty good repair record. Of all the cars that were forced, how many were domestic and how many were foreign? Well, 9 and 9, 50%, 50%. Of the ones that were 3s, 90% were domestic, 10% were foreign. Of the ones that were 5s, 81% were foreign cars. So, assuming that my interpretation of this variable is correct, assuming that a 5 means the car is better, right, that would seem to suggest, just from looking at it, that foreign cars had better repair records, right? Because more of them were 5s, right? There were disproportionately more 5s. And your domestic cars were down here, right? They had all of the ones with the 2 poorest records, and most of the ones that received 3s. Now that's not a test, right? That's just a raw interpretation. But if I were, say, trying to explain this to someone, I would say, yeah, okay, I would focus on this 5s column and focus on this 3s column. And say, in this case, 80% of my best, repair records were foreign cars. And of the 3s, which was the lowest category that had a lot of cars in it, 90% of those are domestic. Right? So that's the first thing that's added. The second thing that's added is actually the chi-squared test, right? So this tests the null hypothesis that these two variables are unrelated. What does that specifically mean? It means that it tests the null hypothesis that your probability of being in one of these two rows is unrelated to your probability of being in any particular one of these columns. Right? So if I'm in column 5, I would be no more likely to be in column 1 than column 2. Right? That my probabilities would be completely unrelated. That's the hypothesis that we're testing. And here we see our p-value here. This PR is our p-value, and our p-value is estimated at 0.000, right? So less than 1%. Actually, probably less than 1/10 of 1%, right? So that means that we would expect to see a distribution like this of these probabilities, these joint probabilities, less than 1/10 of 1% of the time if the null hypothesis were true, right? So we can rule out that these two variables are unrelated. Okay, so that's really all there is to the chi-squared test, right? You basically look down, you see what your p-value is. That tells you whether or not you have a significant result, and then you go into the table itself and interpret some of these differences, right? So one thing that means is that crosstabs are easier to interpret, generally speaking, when you have fewer categories, right? If you have 10 categories on each variable, the crosstab's going to get really messy and can be difficult to interpret. Okay, moving on to the t-test. So let's for my next test, I want to look at foreign cars again, but now I want to look at miles per gallon, right? Gas mileage. And I want to see, do foreign cars get better gas mileage than domestic cars in 1978? Right? So foreign being a dichotomous variable and miles per gallon being a ratio variable, being a, let's actually just take a look at it. Being specifically, technically, it would be a count variable, right? Ranging from 12 to 41. But it's a ratio. It's something you can take its mean. Its mean makes sense. So if I want to do this, if I can take its mean, then I can do a t-test, right? So the command to do this is t-test. Then you put your dependent variable, mpg, comma, by, in the parentheses, and within the parentheses we put our independent variable. So in this case, foreign. Right? So for this to work, this independent variable has to have exactly 2 categories, or there have to be exactly 2 possible values for this to work. So you run this, run that line, and this will give us a t-test. Right? So it's a test specifically of the null hypothesis that these two groups have the same mean miles per gallon, right? So down here it tells us what the null hypothesis is, right? The hypothesis is that the difference, mean of the domestic cars minus the mean of the foreign cars, is 0. It's a fancy way of saying they have the same mean. Right, so what do we observe? Well, we observe from the data that we have that the average domestic car has a mean miles per gallon in 1978 of 19.8, and the mean foreign car had a miles per gallon of about 25 miles per gallon. So what's the difference there? The difference is in this column. It's 4.94, and so the sign on this difference is just going to be the top row minus the bottom row. So Stata sorts these by the value. So here this is a 0, this is a 1, so the 0 comes first. And it just takes this minus this to see what the difference is. So our difference is the foreign cars have about 5 miles per gallon better. So what's the likelihood, right, that we see this in our sample, but in the larger population of cars that these are actually the same, right? Is this significant or not? Well, we go down here, and I always use the middle of these three values. I always use the two-tailed test, which is what this is, unless I have a specific reason not to. So in general, 95% of the time, you'll want to use this two-tailed test here. And so this bottom thing, this probability absolute value of capital T greater than absolute value of little t, that's your p-value. Stata is not very consistent with how it labels p-values. But that probability is 0.0005. Right? So this is, again, less than 1/10 of 1%. So we'd expect to see a difference this big or bigger, less than 1/10 of 1% of the time, if these two values in the population are actually the same. So if we just want to know sort of the 95% significance level, right, we can also just look up here at the test statistic. And if this number is bigger in terms of magnitude than 1.96, so it's either greater than positive 1.96 or less than negative 1.96, that means that we've satisfied the 95% confidence level with a data set this large. Right? This, when we get to very small data sets, right, if our data set is like 20, then we can't actually make that determination just from here. Right? But if our data set is big enough to use the central limit theorem, it's over about 30 or 40 or so, then we can apply what we know about, say, the normal distribution to say, okay, this value will be right around 2 if we have a 95% significance level. Okay? So that's the t-test. That's pretty simple. I would say, if you're in a situation where you can do a t-test, do it in terms of these bivariate tests, because it's probably the simplest to interpret. The third test I want to look at is one-way ANOVA, and so this is what we would use if we say had the same dependent variable. We had a dependent variable that looks like this, but our independent variable had more than 2 categories, right? Because a t-test only works with exactly 2 categories. One-way ANOVA is a tool that's used frequently in experiments, to be completely honest. But at its most simple level, right, one-way ANOVA allows us to have more than 2 groups. Okay. So to execute a one-way ANOVA, the command is one-way. Then we list our dependent variable. In this case, I'm going to go for the price of the car. Right? I want to look at the relationship between the price of the car and its repair record. Right? Maybe I think that cars that have a better repair record will be more expensive. Or at least I would hope that they would be more expensive. So you go dependent variable, then your independent variable, then a comma. And I always set the tabulate option. And this will be obvious in a second why I do this. But you can execute the test just like this and still get your results, but your interpretation will be much more difficult. So I always add the tabulate option. So what happens is the tabulate option adds this little table right here at the top. Okay, so what do we have here, right? So this part down here is the actual ANOVA test. Okay. The this part down here is a separate test, the test for equal variances that I would say most people don't really, unless you're doing sort of a serious ANOVA with an experiment, if you're, you generally don't need to use. This is, a little bit more advanced we're dealing with. And then this table at the top gives us the different means for the various groups, right? So these are in dollars. So the mean price of a car with a repair record of 1 is $4,500 in 1978. With a repair record of 3, it's $6,400. With a repair record of 5, it's $5,900, right? So these are our means. And we have our overall mean down here. Okay. So we can see that this seems to be kind of a mixed bag, right? It seems to get bigger and then smaller, right? We have very few cars in these first two categories, so that could be throwing us off a little bit, perhaps. But we seem to be, that the higher cars might be the better repair record cars, if this is what this variable actually means. The cars that are higher on repair record might be less expensive than the cars that are in the middle, which might be more expensive than the cars that are at the front. We're not sure if this is real. We're not sure if there's any sort of consistency here. It's hard to say what's going on. But we want to see, okay, we want to sort of get a test of, are all of these groups coming from a population that have the same overall mean, right? What's the probability that we see something like this, right, when they all have the same actual mean value, right? So if you look besides this 2 here, right, besides this first category, which only has 2 cars in it, these 4, they're pretty close to one another in their values, right? We're ranging from 5,900 to 6,400, and we're pretty close overall. So what's the probability that all of these actually have the same variance, right? Or what's the probability that we see something like this if all of these groups in the population, if all of your poorly repaired or poor repair record cars and great repair record cars in the population had the same mean price? Well, that probability here is 91.7%. Right? So our F statistic, which is our actual hypothesis test of equal means, and our p-value over here, the probability of F, yet another different way of saying the p-value, is right here. So this p-value of 0.917, this tells us that there's a 91.7% chance, right, that if we saw something like this, it came from a population. Well, a better way to put it is that if we drew a sample that looked like this, right, that 91% of the time we would see a sample that was at least this, far from the mean, right? That was at least this dispersed if all the groups in the population had the same mean, right? You think of it, that what's the probability that we observe something that's at least this wonky? That's 91%, 92%, right? So when you're actually presenting this information, you need to go up and look at these different comparisons, right? So we'd say, okay, a repair record of 5 and a repair record of 2 are pretty much the same, and they're pretty darn close to a repair record of 4. Right? All these cars seem to be about $6,000, with the exception possibly of 3 and possibly of 1, right? It's possible that 1 might be cheaper, possible that 3 might be more expensive, but as our test here says, we seriously can't rule out the possibility. In fact, it's pretty likely that all of this is just random noise based on which particular cars made it into our data set this year. Right? So that's how we'd interpret that. Right? So I hope this was helpful. There are, of course, a million other things we could talk about with these tests, right? There are different kinds of robustness checks that you can do. Again, we're not even addressing Bartlett's test for equal variances. Right, so we're not addressing any sort of extra little things we can do. We're not changing up, the orientations and getting other kinds of percentages and things like that. It's just a really sort of simple first cut how I would look at these tests if I were just running them and trying to make a quick interpretation. So that's all I have. I'll talk to everyone later.